Welcome! In this video, I'll show you how to solve problem 8.12 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. This problem states the following. It says, use the WKB approximation to find the bound state energy for the potential in problem 2.48. And the potential is what I wrote down here. It is minus h bar squared times a squared, which is some constant, over m times the hyperbolic secant squared of ax, and the hyperbolic secant squared. Now, this potential, what does it look like? Well, in general terms, of course, I'm not going to do a very detailed sketch, but it looks something like this. Okay, it is basically this bump in the middle, and then it decays, and something very important, it is even. Okay, it is even. Now, why is that relevant? That is relevant because it's going to, just as in the problem 8.11 that we already solved, it's going to give us a condition for x1 and x2, both of the turning points. Now, what are the turning points? Once again, another quick reminder. The turning points are the values of x, so this would be x2, and this would be x1. Those are the values when the energy is the same as the potential. And since we are in a symmetric situation, the absolute values of x2 and x1 are the same. So basically, x2 is equal to minus x1, or the other way around, x1 is equal to minus x2. Okay, so that is something that we should note. Another important thing, we are in a situation where there are no walls, at least no vertical walls, no infinite walls. So that means that we are in the case that we saw right here. We proved this formula some videos ago. This is the WKB approximation, the result that it gives us for the case where there are no sloping walls. So we get that n, the energy levels, minus 1/2 times pi h bar is equal to the integral between our turning points of the momentum. So basically all we have to do, and that's something very, very often, something that happens very often in the WKB approximation, in fact that's what it is all about, is that we only have to solve one integral instead of having to solve the entirety of the Schrödinger equation. So all we have to do is plug this potential in there and solve the integrals. Now, it is going to be a little bit more difficult than that, of course, because the integral will be a bit annoying, but in principle, that's all you have to do. Okay, so let's begin by finding the momentum. So the momentum is, as usual, the square root of 2m times e minus the potential. But the potential is minus, so we get a plus h bar squared a squared over m times the hyperbolic secant squared. All right. There we go. And, well, there's not too much we can do here to further simplify it. So let's plug it in immediately. So we integrate now not from x1, but rather from minus x2 all the way to x2, because x1 and minus x2 are the same thing because of the symmetry of the problem. Then we have the momentum. We can factor out the square root of 2m, and then we have square root of e plus h bar squared a squared over m hyperbolic secant ax, and square root goes all the way dx. Now this looks a little bit awkward. The energy here, for example, we could just get rid of it. So I'm actually going to, there we go. I'm going to factor it out. So I'm going to move the integral sign a little bit, expand this, and just put the energy in here. So just factor out the energy, so we get a 1 in here. So 1 plus this, me. Okay. So what do we do next? How can we go about solving this integral? So first of all, notice that once again, we are in a symmetric interval. So we are integrating from minus x2 to x2, but the secant square, the hyperbolic secant square, as you can see, is an even function. So that means that we can rewrite this as the square root of 2me and times 2 times the integral, and now from 0 all the way to x2. So the question is, what is x2? Now we know x2 is the turning point. What does that mean? That means that it is the point where evaluated in the potential, so the potential evaluated at x2 is equal to the energy. So that means that the energy is equal to, what was the potential again? I already forgot. It is minus h bar squared a squared over m times the hyperbolic secant squared of ax2. So ax2. There we go. So that is the energy, and this is what basically gives us not only x2, but the secant of x2 in case we ever need it. Okay, so now let's go back here and continue looking at this. So we can just put this here. So 1 plus h bar squared a squared over me, the hyperbolic secant squared ax. So here we have to start thinking, well, how can we possibly solve this? Well, the secant itself is a little bit of a problem. So we might want to attempt something like, let's say our new integrals, our new constant of integration, or variable, sorry, of integration will be z, and we will define it to be secant, the hyperbolic secant squared of ax, which means that we could rewrite this part here as this thing there as simply z. So this is z. But we don't know the x yet. So for that reason, we need to take the derivative of x. Now, I think the easiest way of doing that is isolating x here, so solving for x. So that means that we have to take the square root, then the inverse hyperbolic secant, and then divide by a. So we get that x is, let's see, it is 1 over a times the hyperbolic secant inverse, and then we have z to the 1/2. Now let me double check, because we had to take the square root, which gives us this, take the opposite, the inverse of the hyperbolic secant, and then 1 over a. Yeah, there we go. So to find dx, we will need to find the derivative of the inverse hyperbolic secant. Now you may know that already. The derivative of that, so let's say dy, so that I don't use any of the same letters that I'm currently using. So this will be to the -1 of y. This is minus 1 over y times the square root of 1 minus y squared. So in this case, where we don't have y, but z to the 1/2, we have, of course, this 1 over a in front, which now has a minus sign, and we get times 1 over z to the 1/2 square root of 1 minus z to the 1/2 squared, so simply z. And then we have to multiply, because of the chain rule, times the derivative of what is inside. So times the derivative of z to the 1/2, which gives us 1/2 times z to the minus 1/2. But this and this, they will multiply, so the exponents add up. We get z to the 1/2 plus 1/2, right? Since z to the, this is basically 1 over z to the 1/2. So we end up with this z here being simply z. There we go. And I'm just going to write this 2 in the front. And of course, dz. Okay, so now we can plug that into our integral. So let's begin. So what we had before is simply 2 square root of 2me. And then we have the integral. Okay, we need to find the new limits of integration. So let's do that quickly. Now, our old limits were from 0 to x2. So when x was equal to 0, we had z, or what we have is secant of 0 squared. But secant of 0 is 1, so we get 1 squared, which is still 1. And when x is x2, what we have is, let's see, So that is z equal to the hyperbolic secant squared of ax2. Okay, but just like we did in the previous case, right, we can relate it, and by that I mean problem 8.11, we can relate this to what we saw here in the turning point. Because from here we can see that the hyperbolic secant squared of ax2, this is simply minus h bar squared over a squared times a squared over me. And as you can see, this is precisely what we have here. So this upper limit of the integral is going to be minus h bar squared over a squared me. And this we will simply define as some constant b, so that we don't have to be writing it all the time, but of course in the end we will plug it back in. Okay, so we are now integrating from 1 to b. So now we have the square root of 1 plus h bar squared a squared divided by me, and we still have z. So notice that here, all of this is inside the square root, of course. This thing is basically minus 1 over b. But here I can actually see that the factorization that we did at the beginning wasn't all that ideal, so I'm actually going to improve it a little bit. And because I don't really want to have that minus 1 over b, we can do better than that. So let me multiply through by me, right? Basically undoing the initial factorization. So multiplying through by the square root of me means that this 1 turns into me. And I want to show you this because sometimes you try out a factorization and it doesn't work out all that well, and it's all right. We will simply try a different one. So now let's factor out instead h bar squared a squared. So when we take them out of the square root, we get h bar a, and they will be gone from here, and we have to divide here. So h bar squared a squared. And I'm just going to put a little bit of extra space in between, so plus z. Okay, and now that we did this other factorization, notice that we got precisely minus b. So we don't really have to worry about that 1 over b. So of course, you could have gotten to the same thing with the other factorization, but I think that this is a bit better. It's more concise. So we end up with z minus b, sorry, not minus 1, minus b. There we go. So now let's plug in dx. So dx is right there. dx is 1 over 2a times 1 over z square root of 1 minus z dz. Okay, so here a few things will cancel out. So we have this 2, which will cancel out with this. A cancels out with this. So maybe let's just get rid of them immediately. There we go. And okay, let's just rewrite this one final time and say, okay, n minus 1/2 pi h bar, right? That's where this whole thing came from. This is equal to the square root of 2 times h bar times the integral from 1 to b. Oh, and we almost forgot about the minus sign, by the way. We almost forgot about the minus sign, so thank God I noticed. So minus here and minus here. And this is square root of z minus b over the square root of 1 minus z, 1 over z, dz. But something we can do is use this minus sign to simply flip our endpoints. It doesn't really matter, but you know, you get rid of the minus sign and you don't risk forgetting about it like I just almost did. So that's why I like doing it. Okay, so now we need to solve this integral. Now there's surely many different ways to solve it. I'm going to try something that I like to do here, and I think it's the easiest for me. But of course, if you know a better way to solve it, go ahead. Now, what I like to do is I'm going to just multiply and divide by the square root of z minus b. And why do I do this? Because this will allow us to simplify our expression considerably. So we end up with z minus b in the numerator, times dz of course, and then z square root of 1 minus z, and square root of z minus b. So all of those. And now we can separate this into two different integrals that will each be a little bit simpler than our initial one. So this means that we have one integral that is z dz over z square root of 1 minus z square root of z minus b. And then we have minus b integral from b to 1 of dz over z 1 minus z, and then square root of z minus b. There we go. So these are the two integrals that we need to solve in this problem, right? As usual, the WKB approximation basically gets rid of the need to solve the Schrödinger equation, and now you simply need to solve one or two integrals. Right? I guess it depends on the problem. It is one, but we divided it into more integrals. Okay, so let's begin with integral 1. Now notice, of course, that the z's cancel out, so that makes it much better. So I wrote I1. So this is, of course, I1, and this integral without the b is I2. So I1 is integral from b to 1 of dz, and then 1 minus z and z minus b. Now, how do you solve an integral like this? The way to do it is to choose any of these two. It doesn't really matter. I'm going to choose 1 minus z because it is there first. And you say, all right, u is square root of 1 minus z. We will have to do quite a few substitutions, but we will get there. And let's see, what is dz? Well, we can find it in several ways. I'm going to do it as du. This is 1/2 of 1 minus z to the minus 1/2. And then we have to multiply by the derivative of what is inside, which gives us a minus sign. And then we have dz. So from here, dz is equal to minus 2 divided by, or actually, no, we have to multiply. So we have to multiply by 1 minus z inside of our square root du. Okay, so there we found dz. So now let's plug it in. So let's switch colors again. So we get integral of b to 1 of not dz, but now du, which is minus 2 square root of 1 minus z du. And we are still dividing by square root of 1 minus z and z minus b. And this is why it doesn't matter which one you choose, because the square root that you chose as u cancels out. So this cancels out, and we are only left with this one right there. And what do we do now? Well, now from this expression, we solve for z. So by squaring, we see that, let's see, u squared is equal to 1 minus z. So z is equal to u squared. Actually, no, it's the other way around. It is 1 minus u squared, right? Because you have to add this, subtract, yes. So here we have the integral. Oh, and we didn't change the limits before, so let's do it now. Now, in our new variable u, what are the new limits? So maybe let's do it somewhere over here. So when z used to be b, now we have, let's see. So if z is b, then u is simply the square root of 1 minus b. And if z used to be 1, then we get that u is 0, right? U is 0 because, yes. Okay, so basically we're integrating from 0 to the square root of 1 minus b. You could also just leave your, and I think that I would actually rather do that. So I'm going to leave this as an indefinite integral. And when I'm done, I'm just going to plug everything back in, and then I will just substitute the limits, maybe at z or at u. I don't really know. You can continue doing it, but we are going to do a few more substitutions. So I think I'm just going to undo every substitution at the end and not worry about changing the limits all the time. So anyways, let's see, what do we have? We have minus 2 du, and then we have the square root of z minus b. So let's plug in what we found for z, which is 1 minus u squared, and then we have still the minus b. Now, this integral may not look very easy to solve. Let's take the minus 2 outside. But actually, if we rewrite it, you may have a few ideas. So this is the square root of minus 1. So let me factor out a minus sign. And the square root of u squared plus b minus 1, right? We factor out a minus sign. And of course, the minus 1, it's simply I. So we get minus 2 divided by I. But we can put the I into the numerator by multiplying and dividing by I. So we get minus I up here, which cancels out the existing minus sign. So we get 2I. Okay, so now this integral, we will, whenever we have something 1 over the square root of, let's say, x squared plus 1, we know how to solve this. Right? We can use a substitution of the form, basically x is equal to the tangent of some new variable theta, and we can solve this. We have done it quite a few times already, and I'll show you how to do it again. So we want to get to something like this. So we need to factor out this b minus 1. So we integrate du, and now we have to factor out the square root of b minus 1. Why the square root? Because what we want to have is u divided by the square root of b minus 1 and all of this squared, right? Because we will have x squared, so simply x is going to be u over the square root of b minus 1. And then we have plus 1. Okay, so there we go. And now we actually do the substitution. So I'll get rid of this so it doesn't confuse us. And our new variable will be, let's call it, I don't know, have we used v? I don't think so, right? So let's say v is equal to u over the square root of b minus 1. And thus, the u is going to be the square root of b minus 1 times dv. So let's plug it in. So plugging this in, we get that 2i over the square root of b minus 1 times the integral of the square root of b minus 1 dv divided by, and now here we have v squared plus 1. So these things here cancel out. That's very nice. That's something that happens very often in this sort of integral. And now we have to solve this other integral. Well, how do we solve this? Well, guess what? With another substitution. Now, you could have done kind of two substitutions in one. You could have combined this with what I will do now, which is say, all right, w is the tangent of theta. And notice, this is why I didn't want to have to bother finding the limits of integration all the time, because we were going to do a lot of these. Okay, so dw, this is going to be the secant squared of theta, d theta. And, okay, wait, I introduced too many. Okay, no, this is, let's say v and dv. There we go. I introduced too many new variables. Okay, so this is 2i. Now, instead of dv, we have secant squared of theta d theta divided by, and now we have the square root of the tangent squared of theta plus 1. Now, you may already know what this is, right? That is the secant squared. But if you don't know, I'll just show you. The tangent squared is simply sine squared of theta over cosine squared of theta. And here we have plus 1, so we can take common denominator, and we get sine squared plus cosine squared theta, that is 1. And since we are dividing by the cosine squared, and it is inside of a square root, it ends up multiplying as simply cosine theta. And this thing here is 1, so we get rid of it. And here we have secant squared times cosine. Secant is 1 over cosine, so by multiplying with cosine, we lose one of the secants, so we end up with the integral of the secant. Okay, how do we solve this now? Well, we solve this. Actually, I think I'm going to start writing downwards because I'm going way too much off to the side. So let me just recap here. So currently we have 2i integral of secant theta d theta. Well, to solve this integral, what we have to do, or I guess there's several ways of doing it, but what I like to do is to say, all right, let's now multiply and divide. So this is a little bit of a trick. And what we'll do is we'll multiply and divide by the secant of theta plus the tangent of theta. So we multiply by that and we divide by that. And of course, the theta. Okay, so now that we have that, what we will do is, let's see. So here, what could we do to solve this? Notice we have now, we introduced this secant theta, tangent theta everywhere. But it really didn't make things simpler, at least not at first glance. But now we can introduce another variable, and this I will call w, which will be precisely secant theta plus tangent theta. So what is dw? Well, dw is going to be the derivative of these things. Well, the derivative of secant theta is tangent theta times secant theta, and the derivative of tangent theta is secant squared theta, and all of this d theta. So this is the same, so dw, this is, we can factor out a secant, so secant theta, factor of tangent theta times, or plus, sorry, tangent theta plus secant theta, d theta. So from this, we see that d theta is dw over secant theta times tangent theta plus secant theta. Okay, this of course here is w, but I just want to make this very clear. So d theta, this is dw divided by w times secant theta. So let's plug it in. So let's plug all of this in. So we get 2i integral of, and what do we have here? Well, we have secant theta still, so secant theta, and then we have w divided by w, right? This and this, they are both w, and then we have d theta, which is simply dw divided by w secant theta. So this was a very intricate way because these w's cancel out and these secants cancel out. So this was all just so that we could simplify and cancel out that secant, and now we have integral of dw over w. There we go. And this integral is very, very easy. Okay, this is now something we can solve. So this is simply the natural log. So this is natural log of w. Okay, but we still need to evaluate this, right? We have to evaluate this at our endpoints. So to do that, we now have to begin basically plugging everything back in here. So what was w? Well, w was secant plus tangent. So 2i times, there, times the secant of theta plus the tangent of theta. There we go. And well, what is theta? No, actually, what is it? I don't recall. So theta, we don't know what theta itself is yet. So theta is the inverse tangent of v. Okay, so let's plug it in. So theta is the inverse tangent of v. So here it's going to be easy because we have tangent of the inverse tangent of v. So that is simply v. So that part is easy. That is v. But here we have secant of the inverse tangent of v. Now this may not be all that obvious. So let me show you how you can know what that is. So this implies that we have tangent inverse of v, so arctan of v. This is some angle, right? So we have some right triangle with an angle, let's call it alpha. And we know that the tangent of alpha is equal to v over 1, right? This is simply from here. We applied tangent to both sides. So that means that, and tangent is the opposite side, so this one divided by the adjacent side. So that means that this is v and this is 1, which means that due to Pythagoras' theorem, this is 1 plus v squared. There we go. So why is this relevant? Because, well, now we know that this angle here, alpha, is precisely the inverse tangent. So instead of writing it like this, we write this as alpha, which, by the way, alpha is the same as theta, but I just wanted to show you that too. I didn't want to just make it up and say, oh, this is like this, believe it. Okay, so we just show that. Okay, and what is the secant of alpha? Well, the secant is 1 over cosine, so let's find the cosine of alpha. So the cosine of alpha is this side divided by the hypotenuse, so 1 over the square root of 1 plus v squared. So the secant is 1 over this, so the secant of alpha is the square root of 1 plus v squared. So this thing here is simply 1 plus v squared inside of a square root. Okay, now let me get rid of all of these scribblings here because they were just so that we could show this. Okay. Now, oh wait, where's v? V disappeared. Okay. Now we need to continue. What was v? So let's see, where was it here? V is u divided by the square root of b minus 1. So plugging that in, we get 2i natural log of square root of 1 plus u squared divided by b minus 1. So all of that inside the square root. And then we have plus u divided by the square root of b minus 1. Okay, but what was u? Well, u was 1 minus z, square root of 1 minus z. So that means that this is the square root of 1 plus, and here we have u squared, which is 1 minus z, and this is divided, let's see, by so this thing here is u squared divided by the square root of b minus 1 squared, so simply b minus 1. And then we have v, which is going to be u divided by the square root of b minus 1. Okay, so now what is u? Well, u is the square root of 1 minus z. So this thing here, 2i natural log of the square root of 1 plus, and now we have 1 minus z and b minus 1. All right, what else? And then we have here, so plus the square root of 1 minus z divided by the square root of b minus 1. There we go. And this whole thing, of course, is evaluated between the two endpoints of z. Now that we are all the way back to z, we can actually see what this is. So we are integrating from from b to 1. So this is from b to 1. I guess we could have done it with u. It doesn't really matter. So here this is the situation we are in. But what happens if we just plug it in? So if we just plug it in, we get 2i natural log of, let's see, so if we plug in 1, we get square root of 1. So 1 plus, and by plugging in 1 here, we get 1 minus z, which is 0. So we simply get the natural log of 1, which is 0. So the first endpoint is 0. So we will have minus this thing evaluated at b. So we get square root of 1 plus, and at b, let's see, we have 1 plus 1 minus b divided by b minus 1. So this is minus 1. So we get 1 minus 1. So we get 0, right? 1 minus 1, this is 0. And then here we have plus the square root of 1 minus b divided by the square root of b minus 1. But here it isn't so simple. So we can factor out a minus sign here. So we get basically I times b minus 1, the square root of b minus 1. And this thing is 1. But then we have the natural log of I, and there's a good chance that, we don't really know what the numerical value of that is. I guess you could just look it up. I guess we can look it up, right? So the natural log of I. So the natural log of I, this is, this thing right there is pi over 2 times I. So this thing is, let's see, so the i's, they multiply, we get a minus sign, which cancels out this minus sign, so we end up with pi. So that is one way to solve it. If for some reason you don't have access to that or whatever, you can use something called the arcsine logarithmic formulation, which basically allows you to go from the natural log to arcsine. I made a video showing where you can get this formula, and it basically tells us that minus I, the natural log of the square root of 1 minus something squared, plus I times that same something. This is the arcsine of that something. So what we could do here is simply factor out a minus sign in here. So minus z minus 1, and factor out an I from here. So we get z minus 1, and we multiply by I. And now we have this thing in the exact same form, but we still need a minus here. So we can multiply by minus 2 times, basically write this as minus 2 times minus I and all of this. So by doing this, we can now have minus 2 times the arcsine, so arcsine of, well, in this case, it's not x, it is the square root of z minus 1 over b minus 1. And this is now evaluated between b and 1. So we can now evaluate this, and evaluating the arcsine is a bit more intuitive than evaluating the natural log if you don't have a calculator. So let's see, the first point is at 1, so we get arcsine of 0, which is 0. Then we have minus the arcsine of this thing evaluated at b, so arcsine of b minus 1, so we get 1, so arcsine of 1, which is pi over 2. So we end up with minus minus, which is plus, and we also get pi. So there we go. Just two different ways of getting that result. I would just want to throw this in there in case it's ever useful to you, right? Again, the derivation is in a link in my channel. The video in a video in my channel. The link is in the description. Okay, so that is the result of the first integral. So all of this was just so that we can see that this integral is pi. There we go. Now we need to begin working on the other integral. So I'm just going to quickly make some space so that we can just write without having to bother scrolling too far away. Okay, so just a few stragglers to deal with here. Oh, I shouldn't have gotten rid of that. Okay, so now our integral, so I2, which is this thing right there. So I2 is the integral from b to 1 of dz z 1 minus z minus b. And the procedure will actually be basically the same that what we just did. So to solve this, let's use another substitution. I will do the same as before. So u is going to be 1 minus z, and thus du will be 1/2 times 1 minus z to the minus 1/2 times dz, and a minus sign because of the chain rule when we derive the inside part of this function. So from here, dz is minus 2 times 1 minus z to the 1/2 du. So let's plug it in. Don't bother with the limits of integration. We will do a lot of substitutions again, so I'm just going to undo every single substitution at the end. So yeah, just don't bother. Okay, so we have minus 2, and then square root of 1 minus z. Then we have du, all of this divided by z. But what is z? we can find just as before z from here. So z is going to be 1 minus u squared, right? This goes with a minus, this is plus. Okay, yes. So we get 1 minus u squared, and then we have the square root of 1 minus z, and the square root of z minus b, but that is 1 minus u squared minus b. So here, these two things cancel out. But now we don't have the exact same expression as before, because now we have this additional term. So we need to get rid of it. And the way to go about it is to say, okay, let's say u is going to be, and it's going to be an idea a little bit similar to what we did before. We will say this is the square root of 1 minus b, right, which is what we have here, 1 minus b, times the sine of some new variable v. So that means that du will be the same square root 1 minus b times the cosine of v dv. Okay, so what is this? Let's take a bit of a look here. So minus 2, we put the integral. Du is the square root of 1 minus b times the cosine of v dv. Then we have 1 minus u squared, so 1 minus this thing squared. So 1 minus b times the sine squared of v. Okay, and then we have this other thing here, so square root of 1 minus b, just putting that together, minus u squared, so minus 1 minus b sine squared of v. Okay, now what can we do? Notice we have here the square root of 1 minus b, 1 minus b. So we can factor out 1 minus b, and we get product of 1 minus sine squared of v. And that is precisely why we used this substitution, because we wanted to create this very thing. And 1 minus sine squared, well, this is cosine of a squared of v. So this thing here is cosine squared of v. So cosine squared of v. And now this is what is in here. So in here we have 1 minus b times cosine squared of v. So by using this substitution, we now get rid of this and this and this and this, because of course this square root cancels out the squared here. So all of this goes away, and so does all of that. And now we're only left with this part right there. Okay, and now, well, the question is, yeah, how do we continue? Now we can write the sine of v, which is the tangent of v, right? Sine divided by cosine divided by the secant of v. There's a few ways to go about it. So don't worry about only this one. There's other ways to do it, but I like doing this. So instead of having this sine squared, now we have the tangent squared of v divided by the secant square of v. Okay, and now let's just multiply through here and do a little bit of algebra. So we have minus 2 integral of dv. Okay, and let's see. So here we take common denominator and we get secant squared of v minus, and now let's multiply through. So we get minus 1 times the tangent squared, so minus tangent squared of v, and then plus b tangent squared of v, and all of this divided by the secant squared of v. But since this is 1 divided by something divided by the secant squared of v, we can write the secant squared of v here in the numerator, secant squared of v dv. Okay, now what else do we have? We have secant squared v minus tangent squared of v. Well, what is that? This is basically saying 1 over the cosine squared of v minus the sine squared of v divided by the cosine squared of v. So this is already in a common denominator. So you get 1 minus sine squared of v, which is cosine squared of v. So you get cosine squared of v divided by the cosine squared of v, which is 1. So there we go. This thing right there is simply 1. So all of this is 1. So you get 1 plus b tangent squared of v. So this is now the integral that we want to solve. And it may look still difficult, but we actually made a lot of progress. Because now we have the tangent and we also have the secant squared. And we know that the secant squared is the derivative of the tangent. So if we do another substitution, let's say with w, so w is the tangent of v, then dw is the secant squared of v dv, which is exactly what we have there. So now we can write this as minus 2 integral of, this is dw, divided by 1 plus b times w squared. And now we are in a very, very familiar form. This is almost like what we expect to see in the case of the tangent, or in the derivative of the arctangent. Because remember that if you take, I don't know, dx or something of the inverse tangent x or arctangent, you get 1 over 1 plus x squared, right? And why is this so important? Because that is almost what we have. So all we have to do is use a substitution. Again, something like u is equal to the square root of b times w. So that, and well, in this case, dy would be the square root of b times dw, and thus dw is dy divided by the square root of b. So by having this, we get to minus 2 integral of dy. We can put the square root of b outside. And then we have 1 plus y squared. And there we go. This is easy. This is the arctangent. So this is arctangent of y. But what is y? Y is the square root of b times w. But what is w, right? What is w? Well, w is the tangent of v. Okay, so this is the tangent of v. But what is v? So now we have to continue. What is v? Actually, yeah, what is v? Where is v? Where did I define it? So we hadn't written down explicitly, but from here we can see that v is u over the square root of 1 minus b, and we have to take the arc sine of this. All right, so we just plug it in. So tangent of, and here we have the arc sine, maybe put it as sine to the minus 1 of u divided by, was it square root of b minus 1? I need to double check. So let's see, u divided by the square root of b, no, 1 minus b. Okay, I'm glad I checked. So 1 minus b. So 1 minus b. Okay, and I think we know what the limits, what the bounds for u are, right? Or did we not write it down? I guess we could just go and say that u is 1 minus square root of 1 minus z. So this is square root of 1 minus z. And there we go. We know that we integrate between, I think, 1 and b, or b and 1. Let me check. So is it, okay, there's b and 1. So this is between b and 1. Okay, so now we plug it in. So we have minus 2 over the square root of b. And then we have, I'm going to write it like this. So arctangent times the square root of b times the tangent, so of the arc sine of. And if we evaluate at 1, we get 0. So we get the arc sine of 0, which is 0. So then we have the tangent of 0, but the tangent of 0 and the tangent of 0, right? Since tangent is sine over cosine, this is also 0. So we end up with the arctan of 0, but we just saw that it is 0, so the arctangent, of course, is also 0. So this entire first part is simply 0. Then we have minus the second limit, so arctangent of the square root of b times the tangent of, and now we have the arc sine of this thing. So we have arcsine of square root of 1 minus b over 1 minus b, so 1. And the arcsine of 1 is pi over 2. The tangent of pi over 2 is infinity, right? It tends to infinity. So this, of course, in quotation marks, infinity. And the arctangent of infinity is going to be pi over 2. So this thing, pi over 2. So in the end, the 2's cancel out, and we end up with pi over the square root of b. And there we go. Now we can go ahead and plug it in here. So instead of this thing, instead of this integral, we have, this is the square root of pi divided, so it's pi divided by the square root of b. But there's already a b here, so they cancel out and you get square root of b right there. So by doing this, we can still, one last step, we can factor out, we have square root of 2 h bar, we factor out pi, and we get a factor of 1 minus the square root of b. And of course, this entire thing is equal to n minus 1/2 times pi h bar. So here the pi h bars cancel out, so you get rid of this, and you get rid of this, and we are left with this expression right here. And we know what B is, right? B is the thing that contains the energy. B is this thing right there. And here it is B that contains everything that we need to know about the energy. So B contains the energy. So let's quickly solve for B, or the square root of B. So we can divide by the square root of 2. So we get 1 minus square root of B. This is equal to n minus 1/2 divided by the square root of 2. And then we can add this, subtract this, and we end up with 1 minus n minus 1/2 divided by the square root of 2. And this is equal to the square root of b. And now notice what we have here. This side is always positive because it's a square root, right? It is positive definite. It cannot be negative. So that means that this side also has to be always positive. So that means that 1 has to be greater than n minus 1/2 divided by the square root of 2. Or we can now use this to find a limit for n. So multiplying by the square root of 2, we get square root of 2 has to be greater than n minus 1/2, or square root of 2 plus 1/2 has to be greater than n. So what is this? So let me find the numerical value. So the square root of 2 plus 1/2, that is 1.9. So n has to be smaller than 1.9. So 1.94, etc. But and since n originally can be 1, 2, 3, 4, etc., the only possible value for a bound state is n equals 1. Anything else will not be a bound state. Okay, so if we want to find now the actual energy, let's just go back to this expression and plug in the value for B. So we know that B is, I believe it's minus me divided by h bar squared a squared. And now we solve for the energy. Maybe I'll change colors here and separate this. So now we square everything and we get 1 minus, we know that n is 1, so we get this 1 minus 1/2, we get 1/2 divided by the square root of 2. And this is equal to this thing, but we squared, so we get minus me h bar squared a squared. And now finding the energy is easy, right? So from here, the energy is going to be minus this thing, but that's simply a number. So let me calculate it right away. So that is 0.5 divided by the square root of 2 times minus 1 plus 1. So that is 0.646. So 0.646 squared, of course. So let's square it. So this thing squared. So 0.41 we end up getting. So actually 42 if we approximate. So 0.42. And then we multiply by h bar squared a squared divided by m. And now this is a pretty decent answer, because when we calculated the exact answer in problem 2.48, what we found is that the energy is minus 0.5 h bar squared a squared over m. So we were actually able to find a pretty decent answer without having to actually solve the Schrödinger equation. So there we go. This was problem 8.12. Now, well, that is what we had found previously, right? And yeah, it was honestly the difficult thing here were just to solve the integrals, but the procedure itself is pretty simple. It is just use this equation, solve the integral and plug it in, and there you go, you're done. So I hope that this video was useful to you. If it was, please consider leaving a like on the video, commenting and subscribing, and maybe even checking out my Patreon. So I'll see you in another video. Thank you very much for watching.